Hey everybody, how's it going? Today we're going to do a quick problem of column mohr theory and modified mohr. If you're in machine design, this is something you're going to have to know. So here's the problem. The counter shaft shown has two support pulleys. T2 is 15% of T1. The material we're using is ASTM number 50 cast iron, which you can find in machine design textbook tables. Uniform diameter for static analysis of the side where do the static analysis on the side where sigma x is in tension, which means on whichever side of the shaft here, the sigma x will be in tension, so that it will be a positive. I'll show that a little bit later. So plot the shear moment diagrams for the x, y, and z planes, and then find minimal allowable diameter size for the nearest millimeter using column mohr theory. If a factor of safety is 3.0 is to be maintained, and then repeat that with modified mohr, and then talk about the results a little bit. All the dimensions are in millimeters. Okay, so here's our thing, our design here. We've got two pulleys. This is off at a little bit of an angle, 45 degrees. Spacing is 300, 400, and then 150 right here. I'm reading these off because you guys might not be able to see it, and there you go. You guys can get the numbers off of me. Okay, so first thing I did was I did a basic three-body diagram, plotted all the reactions. I turned the angled pulley equations, or tensions, into the direction. The T here is actually a combination of T2 and T1, as shown over here. So T is T1 plus T2. But they're both going in the same direction, so I can say that. So I'll be able to direct those into the X or Y and Z directions, and then went through and then added this one up, which is 50 newtons plus 270 from up here, as you can see. And then the reactions over here at this bearing. And then just to make it a little clearer, I put the torques down here. I know that TA has to be opposite to TB, so I did it, set it up like that. And then in order for TA to be opposite to TB, I can tell that, or T1, yeah, TA opposite to TB, I know that T1 has to be greater than T2. So that's an assumption you can make, because if T1 is pulling harder, then it's going to rotate this pulley around like this. But if T2 is greater like this, then it's going to rotate the same direction as this TB right here, so it's not going to help you at all. So moving on with that, what I got done is I did the force equations already, and there they all are. You do the sum of forces in X, sum of forces in Y, sum of the moments about Z, sum of the moments about Y, and then the sum of the moments about X, or the sum of the torques, which will be able you then find T1 and T2 from some of the torques, and then you set that back up into MY, and then back up into MZ, and then back up to FY, and then back up into FX, and you get your reactions. I don't want to go through that because that's basic static, so everybody can figure that out. Basically, the total T is 370, and then you guys can pause this video and look at these equations if you have any questions about how that is all done. So, moving on from that. We have to plot the shear and moment diagrams, so I'm going to set this part over here, actually. So you can still kind of see it. But, okay, so the shear moment diagrams, I'm going to do it in the XY plane first. So, the shear is like this. Just do a basic plot here, just like this. So I know that the reaction at O in the Y direction is going to be negative 163. Well, actually, here, let me get this set up here. So this is at a distance of, what was it, 300 millimeters. And then this is moving on 400 from that, so 700 millimeters. And then 150. It's not really to scale, but you guys get the idea. And then right here we have reaction OY. And then we have T sine of 45. And then we have reaction of CY. In the XY plane, you can see it from right here. The XY plane, this T force doesn't have any effect, so we can just ignore it here on this shear moment diagram. Alright, so moving on from there. We know that Ry is equal to negative 163.41. And then we know that T sine 45 is 252. So adding that to negative 163, you go up here to 89.14. Like that. And then you know that's going to be constant all the way along there. until we get to here, and then we know that RCY is equal to negative 89.4. So you know that your shear diagram goes to 0, so you know that works. You get your sum of the forces right, and it makes a nice pretty diagram. So then, doing the moment diagram for that same deal, 300, 700, and 150, doing the moment in the XY plane. We start out with a moment of 0, but then we do the area underneath this shear diagram, which is going to be a negative moment. So we go down like that, and then finding that the area is equal to 163.41 times whatever that distance is, 300 millimeters. 300 millimeters. Okay, and then that will equal 49,023 Newton millimeters. You can see that? Cool. Alright, so we have this down here at negative 49,023 Newton millimeters. And actually, if I had done this, this is actually negative 163, so negative right there. So you know it's a negative slope, and you end up with a negative moment, so great. And then again, since you know it has to go to 0, you can just draw a straight line across from here. And you also know that this is all a positive slope, or positive value, so it's going to be a positive slope down here. And we're good, and you can make that assumption. And if you want to check, fine, but we already did the sum of the force equation. Okay, so moving on to the XZ plane. We start out basic shear diagram, 300, 400, 150. And you can see how these all line up. This just makes it easier doing the shear moment diagrams because you know which point it is all the time. So we start out with ROZ, which is 106. That goes over to there. Then we have the negative T cosine 45, which takes that down to negative 146.35. I know I'm going through this kind of fast, but you can get the basic idea of what happened up here and then just apply this down here with the new reactions. And this is a really long problem, so I don't want to create a terribly long video. So then going up here again, and then the new force of the T, the main force on this pulley over here, comes into play and shows up, and that takes it way up here to 173.45. 172.45. That's the addition of 140 and then 320, which is the force of the T, or the forces on this pulley over here. And then you take that over here, and then RCZ shows up, and it takes you down pretty close to 0. It's actually off by about 1, but it's close enough to 0 to be within rounding error. Okay, and then going on to the moment diagram here. This moment diagram actually requires a little bit more math than the first one, but moving on, anyway, we'll survive. This is actually in the X, and then this is in the Y, and then this is the moment diagram. Okay, there we go. So, the moment for the first one, we have a positive moment multiplied by the area, which is find the area under the curve. We find the maximum value for the moment. That goes up like this, and it is at 31,800 Newton millimeters. I know it's in millimeters. I'm sorry about that. I did that calculation earlier without rounding it up, but you can fix it a little later on in the problem because it's just the power of 3. So this could be 31.8 Newton meters if you want to do it like that. And then moving on to the next deal, we know that we need to find the area under this curve and then add it to that or subtract it from that because it's a negative area. And if you do that, you end up with a line that kind of comes down like this and goes down to here, equal to negative 26,740 Newton millimeters. I'll do that calculation for you over here. So, excuse me. So, 106 times 300 millimeters minus 140.35 times what is this? This area here, 400 millimeters. 400 millimeters, because that's the distance across here is 400 millimeters. And if you do that, you find out that it's equal to negative 267.40 Newton millimeters. So there you go. I don't know if you guys can see that. I'm sorry. It's tough to focus in close enough, but see how that calculation kind of goes. Maybe hopefully my camera focuses. There you go. I'm narrating. You guys know what's going on. And then again, you can do this area calculation over here and find out that the moment actually comes back up to 0. So there you go. So there's your shear moment diagrams in all their glory. You got the XY plane, the X moment diagram for the XY plane, and then the shear for the XZ, and then the moment for the XZ. Alright, awesomeness. So moving on from that, the next part we actually have to do is, I have to edit that out there. Next part we're actually going to have to do is going to 3, 2, 1. Alright, next part we're going to have to do is stresses and shear, stress, strain, shear, all that stuff to find out exactly what the heck it is we're doing. So, in this case with the beam, the sigma x, which is this stress, is equal to the moment max times the radius of the bar over the moment of inertia. And then the shear stress, xy, is equal to the torque times the radius of the bar over j, and j is actually equal to 2I. J is a different kind of constant for shear stress, which is just kind of weird and a weird machine design concept. So let me fix my camera here a little bit. There we are. That should make it a little clearer for you. Alright, so sigma x. We know from our shear moment diagrams right here, we've got a negative 49 Newton millimeters, then we've got a 31 and a negative 26. So out of these moments, we know that negative 49.23 is maximum moment. So we're going to use that in our shear equation, or our stress equation here, which is then equal to negative 49.023 Newton meters. As you can see, I just converted the Newton millimeters to Newton meters here with this, just by moving the decimal point over a little bit. And then R is equal to D over 2, and we're trying to find D using coulomb mohr, so that's going to stay as it is. And then we've got pi d to the 4th over 64. And the reason it's pi d to the 4th is because I z is equal to I d to the 4th over 64. Oddly enough. Now, moving on like that, this is equal to just using all the numbers we can to reduce this as far as we can. Do that with your calculator, you end up with negative 499.34 over d to the 3rd newtons per meter squared is equal to sigma x. So we got that. That's all happy. Okay, so then moving on to Cx, we got tau xy is equal to the torque. The torque we found out earlier, if you look at the stress strain that we did, the torque is actually equal to, excuse me, is equal to 33,000 Newton millimeters. So it's going to equal to 33 Newton meters. And again, D over 2 over J times, which is equal to I2 IV times 2. So it's just basically 2 up here, and so that turns into 32. So it's pi d to the 4th over 32, which equals 168.07 all over d to the 3rd newtons per meter squared is equal to tau xy. Underline those because you're going to use them here. Alrighty. So, moving on a little bit now. Now we actually have to do the principal stresses. So, in order to use coulomb mohr, so we're going to call it sigma A, which can also be sigma 1 if you want to, is equal to sigma x over 2 plus the square root sigma x over 2 squared plus tau xy squared. Close that off. Normally this is sigma x minus sigma y, But in this case, we know that there is no stress in sigma y because it's a bending bar. So we can basically ignore that. Yes. Okay, so moving moving on. Hang on.